Uniform boundedness theorem. So this is very important theorem which is called a uniform boundedness theorem. So this is expected for examination. So it was asked as state and prove uniform bounded principle. Just state and prove uniform boundedness theorem, and also its second name is Banach-Steinhaus theorem. So it's remember the second name of the theorems. Now first understand the statement. So let B a Banach space. So let B be a Banach space, and N is normed linear space. So normed space, or we can say that norm linear space. If Ti, it is a sequence of operator. So Ti is a non-empty set of continuous linear transformation, is a non-empty set of continuous linear transformation, continuous linear transformation of B into N with the property. So with property, what is that property? So that property is Tix. So this is a Tix. So it is a set of Tix is a bounded subset of N for every x belongs to B. So with the property Tix is a bounded set of N for each vector x in B, for every vector x in B. Then my aim is, so that I write in different color. So norm of Ti, it is a set of norm of Ti is a bounded set of real number. So remember this statement. So this is very important result expected for examination. So uniform bounded principle, uniform bounded theorems. So in this theorem, what is the given part? So we are going to start the proof. So first understand the given part. Now given part is Ti, which is from B to N. It is a continuous linear transformation number 1. So let Ti from B to N such that Ti of X is bounded set. So that is given. So just first geometrically understand the concept. If this is a set B, this is a N, so Ti is the linear transformation from B to N. If this is a point X, so this point is Ti of X. So this point is Ti of X. So remember that the member of N is Ti of X. So it is a continuous, or we can also say that it is a continuous linear transformation. So it is a continuous linear transformation. Number 1, transformation. Number 2, Tix. So this is a bounded set. If it is a bounded set, then it has upper limit and lower limit. So remember that. So member of this set we can write in the another form. So because it is a bounded set, so we can write the member of this Tix less than equal to some positive number. Now we define for each positive integer, natural number. For each positive integer n, let we define a set Fn which is equal to X belongs to B such that norm of Tix less than equal to n. Right? So this is for every I. So this is for every I that can be written in the set. So this is a set. So this can be written in this way for every I. So this is a Fn set. Now clearly Fn is a closed set. So we see that it satisfies less and equality. So it is a closed set. But I would like to prove that this is a closed set. Our claim, this Fn is closed set in B. Fn is closed set in B. So this is a closed set in B. If it is a closed set in B, so that is my aim. So to prove it is a closed set, I take let Y is a limit point of Fn. Suppose Y is a limit point of Fn. Suppose to prove closed, Y should belongs to Fn. So it should be belongs to Fn. Right? Now by definition, if Y is a limit point of Fn, so there exists some X, that X not equal to y and norm of x minus y less than delta. So if y is a limit point of this set, so here there exists x belongs to Fn such that it satisfies two conditions. So two conditions mean such that it satisfies x is not equal to y and norm of x minus y less than delta. So this is by the definition of limit point. So this can be because of y is the limit point of Fn. Now, since we know that this Ti is a continuous map, if this Ti is a continuous map, then by definition we have for every x minus y less than delta, it implies norm of Tix, Tiy less than epsilon. So it satisfies this condition. So this is a equation number 1. So this is a definition of continuity. Now this Tiy, now this Tiy can be written as Ti y minus x and plus x. So this is value. So since it is a linear transformation, so this can be written as Ti y minus x plus Ti of x. So this can be written as in this way because it is a linear transformation. If it is a linear transformation, so from this norm of Tiy, which is equal to norm of Ti y minus x plus Ti of x. So this is a by definition, by applying the definition of norm linear space triangle inequality. So this is a norm of Ti y minus x plus norm of Ti x. Now what is x? X is a member of B. X is a member of B and x is a member of Fn. So by that condition, so this is less than n and this term is less than delta. So entire term, this Tiy, so it implies norm of Tiy which is less than delta plus n. So we reach at this place, it is for every I. Now what is delta? So here it is Tiy and Tix, not delta, it is epsilon. So as we take one another step again. So if I write it as, so this is a less than epsilon. So I just take one step another. So this is less than equal to norm of Tiy minus Tix plus norm of Tix. So this is less than epsilon plus n. So that is in the given part. Now what is epsilon? Epsilon is some arbitrary number which is positive and approaches to 0. So since epsilon greater than 0 be arbitrary number. So if it is an arbitrary number, it is very near to 0, it means it approaches to 0. If it approaches to 0, so from this we get Tiy which is less than equal to n for every I. So it implies from this y belongs to Fn. Why it belongs to Fn? Because it satisfies all the condition of Fn. So we take y as the limit point and it belongs to Fn. So it means each Fn is a closed set. Each Fn is a closed set. Now, since B is a bounded set, Tix is a bounded set, so B can be written as union of Fn where n is running from 1 to infinity. Why? Because this B is a bounded set, Tix is bounded set. So if Tix is a bounded set, so Fn is also bounded set when n is running from 1 to infinity. So B can be written in this form. So suppose it is equation number 2. Again B is a Banach space. So since B is Banach space and we know that every Banach space is complete. So it is a complete. If it is a complete, here we will use the bare category theorem. So what is bare category theorem? Bare category theorem, every complete metric space is of second category. So what is bare category theorems? So what is the statement, right? If you did not know about this theorem, so go to the previous class book where it is a bare category theorems. So every complete metric space is of second category. So here we used the bare category theorem. So we represent B as the union of closed set Fn. So bare category theorem, there exists so some Fn whose closure possesses an interior point, that contains an interior point. So by bare category theorems, bare category theorem Fn0 closure contains an interior point, right? So x naught, that interior point, so say that, right? So Fn0 closure, it contains interior point. Now since Fn is a closed set, if Fn0 is a closed set, so it means Fn0 closure is equal to Fn0. So it contains a interior point. Interior point means it contains a some ball. Some ball means, suppose first it contains a interior point. So it means S, with whose center is x naught and radius is r naught, suppose, which is part of Fn0, right? So it implies its closure Sx0 R0 closure is a part of Fn0 closure. Since it is a closed set, so this will become Fn0. So it implies it is a closed set. So it is a closed set of x0, r0, so which is a part of Fn0. So remember this. Now what is Sx0 r0? So just where S of closed x0 r0, which is a set consisting all element t such that norm of t minus x naught, which is less than equal to r0. So this is it. Close. This is, if it is a open, then it is only less than. So here it is of this kind. Now this is the basically part in this set belongs to Fn naught. So remember that values. So in order to, if this can be written as S0, suppose 2, so this can be written as S0, so take it as abbreviated form. If I take some element y belongs to Ti S0, so this is Ti S0. If I take y belongs to this values, it implies what is y? Y is equal to Ti x, or where x belongs to S0, right? And it satisfies the condition of S0. So what is that condition? That condition is norm of x minus x0 less than r0, less than equal to r0. So just see the condition. Any member belongs to this, it satisfies in this way. So if it satisfies this condition, then from this norm of y, that is equal to Ti of x. If Ti of x, so norm of it implies norm of y, which is equal to norm of Ti of x, this value. So Ti of x, what is x? X belongs to S0. If x belongs to S0, then x belongs to Fn. If Fn, because S0 is a subset of S0 is subset of x Fn0 from this. So x belongs to this set Fn0. At that place Ti x is less than equal to N0. So remember that. So here, using that concept, this is less than equal to n0. Why? Because x belongs to S0. If x belongs to S0, S0 belongs to Fn naught, and Fn naught, then Fn naught satisfy this condition. Every element of Fn naught satisfies this condition. Now we already did that. If this is a S0, it is a sphere with the center x0. If I subtract, it is as x0. Now here we get it is a sphere. It is a sphere with the center origin and radius r0. If I divide r0, so it is a sphere with center origin and radius unity. So let S is equal to this values. If we take S is equal to this values, so what is this? It is a closed sphere. It is a closed sphere with center origin, with center origin and radius unity 1 means unity mean 1. So this can be written in this form. Now check that what is TIX. So Ti of S. T is a linear transformation. So this can be written as Ti S0 minus X0 over R0, right? So this is a linear transformation. If it is a linear transformation, so this can be written as nor 1 by R0 bracket Ti S0 minus Ti X0, so this bracket, and this is a nor. Now by using triangle inequality, so it is positive number, so it will be 1 by R0, and this is by using triangle inequality, so this is a bracket, and first is Ti S0 minus plus Ti X0. So I get this value. So this is a in term of plus. Now what is Ti S0? Because Ti X0, it is a subset of Fn0. So this is a part of Fn0. Again, X0 is also member of that Fn0. So this term, which is less than equal to 1 by R0. So this is a N0 plus N0, because both the element S0 and X0 part of Fn0, and it satisfies the condition of Fn0. If Fn0, so TIS satisfy this condition for every n. So this is a 2n0 by R0. So just understand this value. So what we get? We get norm of TIS. Norm of TIS less than equal to 2n0 over R0 for every I. This values. If we write in the vector form, So it is in set form. So first, what is set? S is a sphere with center, origin and unity. So what is S? So S is a set of all y. Yeah, we can use anything. Y belongs to B such that norm of y less than equal to 1. This is a S, element of S. It means from this we can write it as norm of Ti y, which is less than equal to 2n naught by r naught for every I, and norm of this vector less than equal to 1. So that is our part. Now this can be written as, if this is subject to condition of this value, so this can be written as set, this is a set, norm of Tiy such that norm of y less than equal to 1, and this is less than equal to 2n0 by r naught for every I. So it implies this can be written as supremum of norm of Tiy such that norm of less than equal to 1 less than equal to 2n0 by r0 for every I. These values. If we used the definition of norm of Ti, so it implies, what is that? It is a norm of Ti. So this is a less than equal to 2n0 over r0 for every I. This values are clear. So what is norm of Ti? So it is a bounded set. If it is a bounded set, so which prove our result, it implies the set norm of Ti. So it is a bounded set of real number, bounded set of real number. So which prove our result, which prove uniform boundedness principle, yeah, uniform boundedness theorem. This theorem, the second name of this theorem, which is called Banach, B-A-N-A-C-H, Banach-Steenhuis theorem. So it is a second name of this theorem. Sometime it was asked that state and prove Banach-Steenhuis theorems. Sometime it is asked that state and prove uniform boundedness principle. A non-empty subset X of a normed linear space N is bounded if and only if and only if f of x is a bounded set for each f belongs to n star. So what is n star? N star is a dual space of n which contains bounded linear functional. So this is a dual space of n. So F is a basically bounded as well as linear functional from norm-linear space n to field. So it is called a bounded linear functional. So this is our statement of the theorem. So this is related to uniform bounded principle. So again this theorem is very important. Sometime uniform bounded principle is asked in the examination. Sometime this theorem will be asked. Now solution or proof of this result. So just understand, let X is a bounded subset of n. So this is a non-empty subset. X is bounded. So I take first part, let X is a bounded subset of n. So it is my first part, a bounded set. Then there exists a positive number k such that norm of x less than equal to k for every x belongs to capital X, because it is a bounded set. Now for each f belongs to n star. So first understand what is n star. N star is from f n to field. Field may be C or R. So this is a bounded linear functional. So I just write it as functional or linear transformation. For every f belongs to n star, it implies f of x, because it is bounded linear functional, less than equal to norm of f into norm of x, this value. So by using this concept, which is less than equal to k norm of f for every x belongs to capital X. So it implies for this value is less than, so this number, so this is less than infinity, and we can say that this f of x, which is a bounded set. So it is our first part, which is a bounded set, right? So first part is complete, because we want to prove if and only if part. So if x is bounded, then f of x is a bounded set. Now converse part. Now in the converse part, conversely, let f of x, which is a image of f of x, which is bounded set, for every f belongs to n star. Now my aim is to prove that x is bounded. Let x is a set which can be denoted as this xi. So I represented x as xi. So it implies f of x, which is equal to set of f of xi, because it is a linear transformation. So we get this values. Now f of x is a bounded set, so this set is also a bounded set. So this is also a bounded set for each f belongs to n star. So remember that. So f of x is bounded, so this set is also a bounded set of f. Now by using the embedding theorem, the concept of embedding theorem, this f of xi can be written as xi of f. This is equal to this set, this is equal to this values. So this is a bounded set. So this is again bounded set for every f belongs to n star. So this is a bounded set. If this is a bounded set, then it implies where fxi is a functional on n star induced by that vectors. So by uniform bounded principle, so this is a norm of fxi, which is a bounded set of real number. So this is by uniform boundedness principle. Uniform boundedness principle. Boundedness principle. So just see the statement of uniform bounded principle, the uniform bounded theorem. So we get this value. Now again we know that this is equal to norm of xi. So it implies this norm of xi, this set is bounded set of real number. So this is a bounded set of real number. If this is a bounded set of real number, so total set x is a bounded set. So which prove our result.